Hi, welcome back to this channel. In this video, we are going to complete chapter 5.1 Gas. So in the previous video, we focused on the calculation. In this video, we're going to focus on the quantitative part, which we are going to explain the assumption in kinetic molecular theory. And then we also will like to explain about the behavior of ideal and non-ideal gas, which also can known as real gas. So for real gas, they will always obey the van der Waals equation, while for ideal gas, as we already know, it is always obey ideal gas equation. Besides from that, we also will discuss about the condition at where the real gas will behave ideally. Let's start with the kinetic molecular theory, at where also tutorial question number 10a. So there are a few assumptions in this theory. First assumption is focus on the movement of the gaseous particles. They are always in random and also straight line motion. Next, the individual particle or the gaseous particle are neither attracted or repel each other. So in other words, to say there are no attractive force between gaseous particles. Next, when the gaseous particles collide to each other, the energy will remain constant before the collision and after the collision. So in simple words, we can say that the collision is elastic. The fourth assumption, compared to the space of the container, the volume of the gas are very small until we can say that the volume of the gas can be ignored. So that's why we say that there is no volume, or we sometimes say volume of gas always equal to volume of container. The last assumption, the higher the temperature, the higher the kinetic energy, means that the molecule will move faster. Now let's continue with tutorial question number 10b. Under which condition the gas will behave ideally? So let's check the graph given here. So the horizontal line over here is to represent the ideal gas. So when we look at here, there are three temperatures, 200 Kelvin, 500 Kelvin, and 1000 Kelvin. So we will notice the line which is nearest to the ideal gas is 1000 Kelvin, so that we know that the gas will behave ideally at high temperature. Next, look at the other graph. Same case as well. This time we will notice the horizontal line also represents the ideal gas. So now at the pressure, basically at the beginning here, the low pressure here, the gas are behave like ideal gas. So generally we know that gases or the real gas always behave ideally when at the condition of high temperature and also low pressure. Now, let's continue with the wording explanation. At high temperature, according to the kinetic molecular theory, we know that the kinetic energy of the gas will getting higher. So when this happens, the molecule actually will be moved far apart from each other. Once they are far apart from each other, the attractive force between the molecule can be negligible. So means that at high temperature, we are going relate to the characteristic for the ideal gas, which is no attractive force. Then how about at low pressure? So at low pressure, the volume of container is very large. compared to the volume of the gaseous molecule, and again, the volume of the gas can be neglected. So this is also one of the criteria for the ideal gas. At the same time, we also can explain like this, because at the high volume or low pressure, the gaseous molecule, again, they are far apart from each other and cause their attractive force are negligible. Okay, just a reminder, there are two conditions that the real gas will behave like ideal gas. One condition, low pressure or high temperature. So when we want to do the explanation, we will going to relate the temperature with the volume, while the pressure with the intermolecular force, so that we can say that the volume and also the intermolecular force between the gaseous particles can be negligible. Continue with tutorial question 10C. Compare the behavior of gas at high pressure and also low pressure. So in question 10B, we already discussed the gas will behave ideally at low pressure. So and then when we discuss about pressure, we are going to relate with intermolecular force. So at low pressure, the gaseous particle are far apart from each other. So when they are far apart from each other, we have the idea that the intermolecular force or the attractive force can be neglected. So second condition, at high pressure, the intermolecular force, the particles are arranged closer. So when the particles, gaseous particles are arranged closer, means that intermolecular force is significant. Once intermolecular force is significant, so means that the gases will behave like real gas. Last part of this chapter 5.1 gases, we need to know about the van der Waals equation. So van der Waals equation will be obeyed by the real gas. How about ideal gas? Ideal gas always will obey ideal gas equation. So this is the van der Waals equation. If we compare with the ideal gas equation, PV equal to nRT. So you will notice that we need to do some correction over the pressure and also the volume. Now, let's check out the correction for the part of the pressure. As we know that ideal gas has no attractive force. So when the ideal gas has no attractive force, so the gases easier to hit the wall of container. So if the gaseous particle hit the wall of the container, pressure will be asserted. However, in another condition, if real gas has attractive force. So you try to imagine if this is the orange particle, gaseous particle, they are attracted to the purple gaseous particle over here. So means that this orange particle, they are not able to hit the wall of the container. So once they are not hit the wall of the container, less pressure asserted. So when we compare now here, we will get the idea. The ideal gas always have larger pressure compared to real gas. So if we need the real gas behave like ideal gas, we have to add something over here. This is the correction part for the pressure. Next, we are going to discuss about the correction for the volume part. So as usual, we know for the ideal gas, the molecular size can be negligible. Therefore, the volume of the gas will always equal to the volume of container. The other way happens to the real gas. When it is the real gas, the molecular volume is significant. Once the volume of the gases is significant, so we are not able to say that the volume of gas equal to container. So the space or the volume that can free moving by the gases will be this area. But the volume of the container is over this part. So that's why we have to do some correction by minus the NB, which is this one, which I highlighted with the yellow part here. Basically, we are not going to do calculation part for the van der Waals equation. However, you need to know what is the meaning of the value of A and B in the van der Waals equation. So, the greater the A value means that the stronger the attraction force between the gaseous particles. So, when we look at here, CCl4 has the largest or biggest molecular size. So, and then all of these are non-covalent compound. So we know that non-covalent compound will possess London forces. So the London forces will be affected by the molecular size. The largest the molecular size means that the London forces are the strongest. So when we compare helium, argon, hydrogen, oxygen, carbon dioxide, and carbon tetrachloride, we will notice the size for the CCl4 is the largest. Therefore, the intermolecular force or the London force among the CCl4 molecules are the strongest. So that's why the A value is the largest in this case. So how about the B value? The B value is indicate the molecular size. So again, the greater the B value, the bigger the molecular size. So if we compare over here, roughly look at the smaller size is hydrogen or helium. Then you will notice their value 0.02 is the smallest among the element or the substance in this table. Last tutorial question, question 11. A group of matriculation students carry out an experiment to determine the relative molecular mass. And then the table shows the result, which consists of pressure and also density. So because this one is involving the calculation, so basically we will try to relate with either Avogadro law, Boyle's law, Charles' law, Dalton's law, combined gas law, or ideal gas equation. So from this question over here, we notice that the question asks us to look for the relative molecular mass and the question given us the density. So these two parameters can be rearranged from the ideal gas equation. So we are going to use PV equal to nRT, and then we're going to expand the formula of number of mole at where is mass over molar mass. So end up you will get mass RT over molar mass. Okay, then because of in the table here the data given is pressure, so basically we know that this one will be the y-axis. So I will rearrange the PV equal to mass RT over molar mass to P equal to mass RT over volume multiplied with molar mass. Then the density basically will be the x-axis. So and then we can see this mass over volume is represent the density. So means that density RT over molar mass. Then we are going to rearrange again so that P equal to RT molar mass multiplied with density. So this is the Y equal to mx. So later when you plot the graph, you will notice that you supposedly will get the linear line. Then to determine the molar mass, you need to find the gradient. So gradient is equal to RT over molar mass. So molar mass will equal to RT over gradient. So when you substitute the value in, you have to make sure the R value is 0.08206 liter atm per mole per Kelvin. Okay, why we choose this 0.08206, not the 8.314? Because the pressure over here is atm, and then the unit of the volume in the density is liter. Then again, also don't forget the unit of the T have to change to unit of Kelvin. Okay, after you plot the graph, the molar mass that you identify will be around at 54.3 gram per mole. But again, don't forget the question is asked us to looking for relative molecular mass. So you are going to use mass, the formula, mass of one molecule gas over 1/12 multiplied with mass of 1 atom carbon 12. So end up you will get 54.3 AMU divided by 1/12 times 12 AMU. AMU and AMU cancel out, 12 with 1/12 cancel out, so we will get 54.3. So we already finished chapter 5.1. So in next video, we will continue with 5.2 liquid. Thank you for watching this video.